and kick it off. Welcome, everyone. My name is Chris Gilman. I'm the Swagelok, Western New York Business Development and Marketing Manager. Thank you very much for attending today's presentation, Valve Sizing and Selection. Just a couple notes before we begin. As you've probably noticed, we have the cameras and microphones disabled since we are recording this, so we'll definitely share this with everyone after the presentation. But please feel free to use the chat function as Nick has been doing during the presentation and submit any questions that you do have, and during the breaks we'll get to those. And also, of course, at the end of the presentation, we'll have a question and answer period as well. So now on to the presentation. As you can see on your screen, Derrick DiCesare, our regional field engineer, is today's presenter. Many of you are probably very familiar with Derrick, as he is our on-site technical expert and therefore engages with customers across our footprint. He's been with Swagelok, Western New York for over 16 years, and aside from, or in addition to being our fluid system expert, he's also a member of Swagelok's global pressure regulator subject matter expert team as well. So without further ado, I will turn it over to Derrick for the presentation.
Got to unmute myself, otherwise this is going to be a short presentation. Thank you, Chris. So again, I am Derrick DiCesare, and we're going to be talking about valve essentials today. And as Chris already discussed, you are going to be muted, so if you do have questions, please type them in the comments and we will get to them either throughout the presentation or at the end of the presentation. And in the event that you need me outside of this, here's my contact information between email and phone number. I would appreciate if you didn't call right now, because I won't be able to answer the phone. But at any point after this presentation, if you have application questions, not limited to valves, but anything else, please don't hesitate to let me know. I'd be happy to get back to you. So for this class, this is what the overview of the class is going to entail. If there's anything right up front that you want to make sure that we address, please let me know so that we can address those. We can answer those questions. Outside of that, we're going to review the 5 different types of valve operation. We're going to review different system parameters and selection factors that are going to affect which valves we're going to be choosing. We're going to go through valves by type. We're going to go through some other valve sizing techniques, and then review some valve options and accessories as well. It's not going to be a holistic list of options and accessories, but more the most common that we're going to run into in industry here. So, real quick, if there's anything that you guys want to know about, if there's anything you want to make sure that I address, again, please let me know. Please add that into the text box so that we can take care of those, as well as any challenges that you're facing, either in selection or performance or otherwise. We want to make sure that we have those listed so that we can address them throughout the presentation. When we look at valve function, there's really 5 different control modes. And what we mean by control modes are what we want this valve to do in our system. These are the symbols that are traditionally associated with those 5 different functions. Some you are almost certainly familiar with, and some you may not be, but we're going to go through them real quick. The first one is going to be an on-off valve or an isolation valve. Second, we're going to have a flow control valve. Third is going to be a directional flow valve, or in this case, a check valve. Fourth is going to be overpressure protection. Number 5 is going to be an excess flow protection. In terms of which ones you've probably seen most frequently, that would be 1, 2, and 3, with 4 and 5 being your less common, not only applications, but certainly symbols. The overpressure protection symbol or relief valve symbol, I don't see on too many diagrams. It's usually something else that looks a little bit different, but that's what we're looking at. To review what each of these different functions, we'll start with our on-off, our isolation. The purpose of an isolation valve is really two purposes. You're going to stop fluid flow or you're going to restart fluid flow. That's it. There is no in between. There is no throttling. This is purely an on-off valve. So traditionally, your isolation valves can be one of a couple kinds. Your most common is going to be a ball valve, followed by a diaphragm valve. But there's some other valve series as well that can accomplish this valve function. That could be a plug valve, could be a needle valve, or bellows valve as well. So depending on the gas, depending on the media, your system pressure, etc., some of these are going to be better suited for this function than others. When we look at a flow control valve, purpose of this is going to be to regulate flow, to have some intermediate step between wide open and off. So this is where you're able to adjust what kind of flow you're getting through the valve. So traditionally, this is done through a needle valve or sometimes a metering valve for your fine flow control. It also can be done with bellows valves and to a smaller extent, plug valves. Those also have a consideration for flow control outside of just on-off. The third function is directional flow control. This is going to ensure that you have fluid flow going in the direction that you want it to go. So as we were showing from this previous symbol here, being a check valve, this is preventing backflow in the system. So as you traditionally flow this way, it lifts the ball off the seat in this diagram, and then your backflow actually reseats the valve. This symbol up here is a three-way valve. So this allows us to take a single process line and then direct it to one of two other side ports, auxiliary ports. So this multi-port ball valve, this one is a 3-port, but there's a 4, 5, 6, and a 7-port ball valve as well. We also have multi-port bellows valves that have some switching functionality. We look at overpressure protection. The whole point of this is to relieve any excess pressure in the system, and that's to keep any of the other instruments traditionally. It could be a gauge, could be a transmitter, it could be a transducer, any of those. You don't want to overpressurize them for risk of damaging the components, as well as to keep the rest of the line safe. So again, traditionally this is a relief valve, but there's also an option for a rupture disc, which we'll talk about a little bit later, which technically is classified as a valve, but depending who you talk to, they may also classify that as a fitting. And the last valve function being excess flow protection. This is designed to control or to contain rather an uncontrolled release of system media. There's an assumed pressure drop across this valve. If that pressure drop increases, the valve will seat itself so that you don't dump the rest of the system media out of the system or have it continue to go downstream. And we've got a nice video to show afterwards of what this actually is going to do later on in the presentation. So at this point, these are the 5 main valve functions. Pretty simple, pretty straightforward, but just want to stop real quick, see if there's any questions or concerns of not only what we're going to cover, but anything that you've heard up to this point. Okay. So when we're selecting a valve, there's a couple of things we should be paying attention to. So what we want to cover, what system parameters and valve requirements should we be paying attention to, and which ones do we not need to pay attention to? So it's difficult to ask a question of 20 or 40 participants, but in general, when you're looking for a valve, there's a couple of things that should jump right out at you is, hey, I need to know if the valve can handle these parameters. And our most 5 common parameters are going to be the system pressure, the system temperature, what's running through the valve, which would be the system media, the flow that's required of the valve, and then what's the environment? Where is this valve going to be placed? So what we're seeing in these 2 pictures here is really going to be with regard to the environment. And I hope we're not running a system through a fire test all the time. Hopefully you're able to space this valve out a little bit more and not just cook it. But we want to know if it's near high temperature, if it's cold temperature, indoor, outdoor. And we also want to know where the valve is going to be placed. Is it going to be on a panel? Is it going to be able to be reached by a technician, by an engineer, by somebody else to be able to manipulate it? Or do we need to go to a different style of valve to make sure it can still be operated regardless of where that valve is going to be placed? So those are the main 5 that we're going to be paying attention to. There are more, and these are other valves, pieces of information that are nice to know. Are they able to be maintained, or is there a maintenance schedule already set up for these? What is the valve cycle expectation? And then how do you define a cycle? Is it one on-off? Is it one cycle of production? How are you going to actuate the valve? What size is the valve? And this one, you could argue, would be up here as well. Is it 1/4 inch? Is it 3 inch? What's the cleanliness of the system, and therefore the cleanliness of the valve? Obviously, safety is inherent to that. I don't think anybody is going to call up and say I need a ball valve, but I don't care if it's safe. But we want to be aware of making sure that we're accommodating your system pressure and temperature and all these other considerations safely, and we're not running them right to the edge or a couple of % over what's rated. And then cost and availability, obviously, are also factors when we're looking at valves. Other things that kind of may be a lesser thought than these main 5 performance considerations. So pressure and temperature, these are the big 2. And anybody that's ever called asking for valve sizing assistance and has been lucky enough or unlucky enough, depending how you want to think about it, to speak with me, this is going to be one of the first couple questions I'm going to ask is, what's the system pressure and what's the temperature? Most Swagelok valves are going to have stamped in the side or etched in the side of the valve a couple of pieces of information. This is a 40 series valve, which is a ball valve. We're going to list the maximum pressure at 100 degrees Fahrenheit, and then we're also going to list the maximum pressure at the maximum temperature that this valve is going to be rated for, in the event that there's some derating of a pressure as we increase the temperature. So it's important to know that on a valve, it can be stamped right on it, what the maximum pressure is, what the maximum temperature is. In the event that you put it in the system and then take it out and throw it in a bin, and then 2 months later come back and say, man, I need an isolation valve. Here's one. I think this will work. You can double check it because it should be written someplace on the valve what our maximum working parameters are of that valve. So we don't accidentally put in a 100 PSI valve where we really need to see 3000 PSI. We want to make sure that from a safety standpoint, you know what the component is that's going into the system. The Swagelok literature has published pressure and temperature ratings. We do this in a couple of different ways. Not all valves are going to be shown graphically like this, but for sure, all of our valves are going to be in a table form. So what we're seeing is at our lowest temperature, and as we increase the temperature, you're going to see the resulting system pressure that this can handle. And what you're going to notice is as we increase the temperature, we reduce the system pressure that the valve is capable of. This particular valve is broken out by valve material, whether it's 316, whether it's Alloy 420 or 600, which is your Monel, Hastelloy, and Inconel. Each of these is going to operate a little bit different. You're going to see some similarities, but ultimately, with any valve, as we increase the temperature, we're going to reduce the potential that valve is going to be able to hold back pressure. In this particular catalog, we show this one graphically as well, just so you can see how gradually the valve performance drops off as we increase the temperature. Every manufacturer should have this information available. If they don't, I would strongly suggest not ordering the valve through them, because you don't know what you're getting into. You don't know what the performance can be in elevated system parameters. So we're going to start looking at ball valves, being the most common valve in the most common application. We're going to take a look at some of the ball valve components. So this is a cutaway of our 60 series valve. 60 series is our 3-piece isolation valve. There's a lot of components shown in here, but we're going to simplify it by just highlighting some of our key components. Number one being the handles that you can actuate the valve. You have packing, and this is going to make a seal between the valve stem and the atmosphere. You're going to have the valve body, which is the center section. You're going to have the ball of the ball valve. That's going to reside right in here. You have the end connections. In this case, they're end flanges. They are separately machined from the body. Those are two discrete components. You have the stem, and you have the packing nut. So the stem interfaces with the ball. That's what allows the handle to actually be able to turn this ball. And the packing nut is what's going to apply pressure to the top of the packing to maintain a seal between the inside and the outside, the process media and the atmosphere. Again, there's a lot of other components in here, but in general, that's what we're looking at for a ball valve, is that you have a handle that actuates a stem that attaches to a ball. The ball is inside of a body. You have end connections that are connecting to the system. And then you have packing and a way to adjust the packing to make sure that you don't have an outboard leak. But not all ball valves look the same. So again, this is our 60 series. This is a 3-piece ball valve. This is our 40G. This is a smaller ball valve. So you're seeing immediately a difference in construction. You're seeing the body, the end connection is a little bit different. This one is our 83 series and our SK series. So we've got 4 different ball valves, all doing the same function, all providing on-off functionality. But the way that these are assembled, the number of components that are used inside of these are different. So why are they different? Well, they're serving different functions. So you've got lower pressure valves that have simpler materials of construction, simpler packing designs. And then for our higher pressure applications, we have to do some redundant stacking of seals to make sure that at 6,000 PSI, at 10,000 PSI, we're able to keep this ball where it needs to be, we're able to keep the media where it needs to be, and we're not introducing a potential leak path through mechanical screw threads, through other end connections. If you look at all these components in here, there's redundant seals everywhere to make sure that if there is a leak past this first O-ring, it gets caught by the second O-ring and then the third O-ring. Trying to keep it as safe as possible, keep the media where it's supposed to be. But each valve is designed for a different application, whether it's general purpose or whether it's high pressure. And as we talked about, there are a couple different methods of construction. The 3-piece ball valve, you'll recognize those by bolts that are connecting the end screws to the body. There's a 2-piece style. Typically, you're going to have this side threading into this main body. These tend to be your less expensive general industrial valves. Usually they're rated to a much lower pressure than these 3-piece valves. But they have a purpose. There's a single piece valve, that's our 40 series, so everything is kind of assembled from the top down instead of the bottom up. And then you have an end screw design, so your end connections, instead of being flanged like this one or integrally machined in the single piece, they're actually threaded into the body. And that's where you have your other components stack up in here. Where you have your seat, your backup rings, and other end connection seals. So all 4 of these are ball valves. All 4 of them are doing the same function, but they are made with a different method of construction. When we look at a 3-piece floating ball valve, the difference with this is the ball is not directly, it's connected, but it's mechanically connected. It's not a single piece ball and stem combination. So the ball floats inside of the ball valve cavity. So this allows it to compensate for a couple of things. Wear, it's going to account for any kind of pressure changes or temperature changes. We think of this being in an off orientation. Right now it's open. If it were off and you had high pressure on this side and low pressure on this side, you've got a high pressure differential across this. what you're going to see is this ball is going to be forced against these seats. If it was a single piece, it's not going to be able to deflect like that. So what you could end up seeing in a single ball and stem combination is you could see something deform. You could start to see this come off center a little bit, or you could start to see leakage across this. By having a floating ball, you're able to compensate for that higher pressure differential across it. And this also allows for an easy rebuild of the seats. Ball valves inherently have a limited shelf life or function life. You've got a highly precision manufactured stainless steel ball that's making a seal against a much softer, high performing plastic. Could be a Teflon, could be a PEEK. Stainless is always harder than this plastic. And over time, in order to maintain the seal, you've got a pretty tight contact surface. This little knife edge that we've created over time is going to start wearing against that seat, and you're going to have to replace those. So with this floating valve design, you're able to remove this end flange, put in a new seat, and reinstall and get back to running your process. On a single piece or some of the two pieces, you're not able to do that. It's not able to be easily rebuilt, and you don't have that simplicity. It's much more complicated, or they're disposable at that point, disposable valves. So we're looking at selecting a ball valve. There's a couple of things within this. Features and benefits. So it's a straight through flow. That's going to be your highest flow valve that you're going to be able to acquire. And it takes up a relatively small amount of space. Ball valve is going to be a quarter turn on off. You think of that ball, you've got a drill port right through the center of it. So rotate that 90 degrees, you're going to go from open to closed or vice versa. Because of the simplicity, it is going to be a lower cost valve. There's less components in there. As much as the cutaway of those look very complicated, they're actually very simple by comparison to some needle valves, bellows valves, etc. And then to automate those, because it's only a 90-degree actuation, the actuator is very simple as well. So we don't have to worry about a linear driven positionable valve actuator. These are just 90-degree on-off actuators. We already talked about the ability to replace the seats. And with a ball valve, because the handle extends farther to one side, you can see pretty easily whether the valve is open or closed, and you don't have to be right next to the valve. It's going to be much tougher to identify orientation of a valve if it's a needle valve, if it's a rotary valve. But with a ball valve, you can see it really easy, whether this valve handle is in line, identifying open, or whether it's perpendicular to your system flow, which would be closed. And with most actuators, there also is an ability to see that as well. So for this style of actuator housing, there's actually a little puck on the top that rotates with the valve stem. So right now we're in an open condition. When this actuates 90 degrees, these little notches in the actuator are going to flip, and that's going to identify it as closed. It's a little bit tougher with these, unless you've been staring at them for a while, to identify these as open or closed. Any questions on ball valves before we move into needle valves?
Nothing in the chat, Derek.
Nothing in the chat, okay. Well, let's talk about needle valves. Similar to a ball valve, we're going to look at some of our key components, and we simplified what this sketch looks like here. In this cutaway, we've got a packing nut, and that's shown by this darker gray figure right there. We have the bonnet of the needle valve. We have the stem. We have the body. There is packing. There's a stem tip. There's a seat. There's an orifice that's created. I'm going to move that arrow. Oops. There's a handle. which has fallen off of there. So these are your main components. So this body has integral end connections. Almost every needle valve is going to have that. The ends are going to be integrally machined to the valve body. The seat traditionally on a needle valve is not a separate component. It's simply a surface of the needle valve that we're going to be making a seal against. And the orifice, therefore, is going to be really just a space that's created between the stem tip and the seat. The orifice technically is not here because we're going to reduce that further between your stem tip and the seat. Packing, very similar to a ball valve, is maintaining the seal between the stem and the body to make sure that our inside process doesn't escape to the atmosphere. And the way that this is drawn also, just which we'll get into in a little bit, the definition of what the bonnet is compared to the packing nut. This packing nut technically should be farther down here, so it's making contact with the packing and not floating and leaving this cavity open in here.
Derrick, could you just touch on flow orientation?
Sure,
The importance with these.
That's a good point. So a ball valve, as we looked at before, is kind of wide open. You've got a straight through flow path that's not restricted, which means that a ball valve technically is bidirectional. So you could flow it left to right or right to left and not impact the performance of the system. A needle valve is directional. And what we're seeing in here, it's not a straight through flow path, even though you have an inlet on one side and an outlet directly in line with it. The actual flow path does this little hiccup in there, and we call that a globe pattern. The way that this runs right now, our inlet is on the left side and our outlet is on the right side. So we direct that flow in line with the stem and then have the outlet go downstream. If you run it the other way, if you run a needle valve backwards, and all the needle valves are going to have a directional arrow on them, so we know which way to install them into the system. If you forget and you accidentally have the arrow pointing towards the inlet side instead of the outlet side, and you send the high pressure this way, there's a risk that over time we start side loading the needle of the needle valve. So this entire stem can become side loaded, which means that we're not able to maintain as robust a seal against our seat here. From a flow performance, it's going to be pretty similar, but from a wear standpoint, you're going to see much more wear if we start side loading the stem. It's a good question. So we're going to look at two cutaways of Swagelok needle valves. The one on the left is our 1 series. The one on the right is an N series. And there's a couple of differences in here. The stem tip is shown as different, a V stem versus a ball stem, and really either of these could be interchanged. The main difference between here that we're going to see is where the packing is located and how the valves are constructed. So the 1 series is it's an integral bonnet needle valve. What we mean by the bonnet of a needle valve is where the stem threads are located. So our actuation stem threads are integral to the body of the needle valve. That's what the integral bonnet means, is that the actuation stem threads are integral to the body of the valve. When we do that, one of the challenges with this valve is that this stem thread is lubricated and there is no seal between those threads and your system. So depending what your media is that's running through it, those stem threads are wetted, and that lubricant, which is not globbed on there, but over time can get washed out and actually contaminate or get into your process media. For some applications, it doesn't matter, and a lot are okay with that. For others, we need to be sure that whatever lubricant is used in this is appropriate for the system, whether it's FDA compliant, whether it's a non-hydrocarbon, etc. We need to know where that potential contamination is. And when we look at where that packing is, the packing is above that actuation thread. So we are still maintaining that system media inside of the valve, but we're also allowing it to make contact with all of these wetted surfaces inside of the valve. So Liquids especially have a higher tendency to wash out a lubricant, but gases over time as well. You can see those lubricants start to migrate again over time. It's not going to be an immediate thing as soon as you put it in. It's going to end up in the system, but we need to be aware of the construction and if that is a concern. So when we look at an N series, again, the bonnet, instead of being integral to the body, if we look at the body in here, there are no other threads. You've got this external thread that's holding this upper portion together. So your bonnet is actually up here. So the N series is a union bonnet construction. Our actuation threads are in a separate coupling that's held together by, in this case, a couple of unions to maintain our seal. So with this, again, our flow path is pretty similar, but our actuation threads are isolated from the system media by this packing. So any liquid, any gas that we have is stopped at this point instead of back here. So from a cleanliness standpoint, the N series is a cleaner valve. And because of the method of construction, this also allows it to hold a higher pressure. There's a lot of different, not a lot, there's a couple of different stem options, this being a ball stem for just on-off applications. I'm jumping ahead because I think it's this slide here. A couple of different stem choices. So the ball stem is designed for on-off only. We don't want to try and regulate flow with this and not have it all the way open or all the way closed. This is going to give you that metal-to-metal seat. The ball actually is able to rotate a little bit. So when you're tightening that valve, if we go back a slide here, when you're tightening this handle in here, that ball is able to make a seat and not create a rotational galling force compared to a V stem or a regulating stem tip. So for this, the tip is directly tied to the stem. So as you try and tighten this valve more, you're grinding this sealing surface together. So we create a galling force. So be careful. The handles are designed so that we don't over torque the valves open or closed. But the ball is able to rotate so we're not creating a twisting force during shutoff. And also the ball is not technically a ball. The top portion of it is machined flat. So that we're creating a common sealing surface, and so the ball doesn't start rotating around. Over time, this can start wearing, and if you do throttle it, there's a chance that the ball starts rotationally spinning, and you'll know that that's happening because it starts getting very loud. So we want to have this all the way down, shutting the system off, or all the way back, getting out of the way. When we look at a regulating stem, this is more traditionally what we would see in a needle valve designed for flow control. You're going to see a slight taper on here, and then you're going to see, in addition to pressure and temperature curves, you'll see a flow coefficient curve. This is going to allow us, when we size a needle valve for flow, we're going to find out what flow coefficient we need. And then we'll be able to go to these charts and say the 0.8 that I calculated, not only is it achievable, but it's going to happen at about 3 3/4 of a turn, or it's going to happen at, in this case, 7.5 turns to open. Most of these are going to have a nice linear relationship. You're not going to see something that's going to do some weird S-bend or a different hiccup. And as we taper out all the way up here, the valve is wide open, and we're not effectively changing any other orifice through the valve. Regulating stem, it's not recommended for repetitive gas shutoff, and the reason for that is, as we previously discussed, you've got a fixed metal stem that's going to go into a fixed metal seat, and the risk of galling in repetitive shutoff applications is going to be pretty high. If we're consistently trying to get this to seat, we're just going to start wearing away at the stem or the seat, and we're going to create a burr or something else that's going to create a leak path across it. But we also have a soft seat regulating stem. So this puts a softer Teflon on this back shoulder here. So we're actually seating on between the Teflon and the seat instead of on the stem tip. So this still is going to give us the benefit of flow control, while also allowing us to shut off in gas services, because we're going to be sealing on this Teflon instead of an all metal seat. Certainly there's some limitations when doing that because it is a Teflon. We're going to have the inherent temperature limitations of that. Metal's able to see a much higher temperature than Teflons are. So again, when we're looking at other design considerations, needle valves are designed for flow control. They're predictable. They're easy to set because of that linear relationship between flow coefficient and number of terms open. We do need to pay attention to any seat and stem wear. Unfortunately, with a needle valve, you're not able to see any of that. What you're going to see is changes downstream. If you have a flow meter, if you have some other means of identifying either pressure drop or flow changes. Over time, if you start seeing that device give a different reading, you know that something's going on either at the seat or at the stem, that you're not getting that same predictable orifice that you're trying to set. Needle valves are available in a variety of materials, and we have options for very high temperatures and different chemicals as well. So if stainless is not going to hold up, we have other materials of construction. Like I was showing earlier, there are Hastelloy, there are Monel, there is Inconel. And if it needs to be something other than those, we can get into that as well. And we want to be aware of what materials are wetted. So if there's concern of compatibility or material washout, we want to know where the bonnet is. Where are those actuation threads? Are they in the system media or are they isolated from the system media? Because that ultimately is going to determine the cleanliness. This valve in the middle here is a metering valve. That's where you're seeing that very fine needle-like stem. This is for fine metering applications compared to this much coarser V stem tip. So it's designed only for flow control. This is not able to do on-off applications. It cannot isolate. You look at the surface area in here, you're going to create a very high friction force trying to close that. And usually what you see is you'll be able to close it, and when you reopen it, it snaps right here. So this valve, as delivered from Swagelok, is not capable of seating. There's a travel limiter set by the handle that prevents it from engaging with that valve body, so that without tampering on it, you're not able to break that stem off. But if you decide that you want to get a little bit less flow, you can tamper with the handle and risk shearing that stem off. And when we look at those, again, we're looking at different styles of stem packing. Some are O-rings, some are going to be Teflon. This is a chevron packing, similar to what's seen in our 60 series, and also the stem tips as well. Ultimately, when we're looking at a needle valve, they're slow opening. To get a valve wide open through 8 turns, if you think of what it would take to actuate a valve 8 turns, you can't get to wide open very quickly. So if we need a system that opens slowly, maybe it's oxygen, maybe it's hydrogen, that we don't want to just send a full shot of system pressure downstream, a needle valve is a great choice for that. Again, we want to pay attention to where the stem threads are because of the potential of lubricant washout. And there are different stem tips. This one that we didn't talk about is just a soft-seated on-off. There is no flow controllability in this. This is a pure on-off valve with a soft seat instead of the ball stem tip. So when we're looking at a valve, after we decide what the flow coefficient is, and we'll talk about that calculation in a little while, after we figure out what that flow coefficient is, we're able to then identify which valve is appropriate based on published literature. So either flow curves or other valve detail that tells us this valve is going to be enough to be able to get that flow through the valve. We're talking about, there's a lot of different valve bodies, and we didn't even list the high-performing alloys, your Inconels, Monels, Hastelloys, Super Duplex. We do list PVC and CPVC because that's a needle valve option. And our internal components, usually it's a Teflon, so either a virgin or reinforced Teflon. PEEK is another very common one, and we have Grafoil on our seals as well when we get into high temperature applications. So if we have to get to 800 Fahrenheit or 1200 Fahrenheit, we can accomplish that with Grafoil, where Teflon, the upper limit of Teflon is usually around 450 Fahrenheit. Any questions on needle valves? Or ball valves? Everybody all right?
Looks like it, sir.
All right. So we're going to talk real quick about the actuation method. In this case, we'll start with manual valves. That's going to be our most common traditionally. Normally for manual actuation, we're going to see either a lever or a bar. It could be a round or oval for needle valves. There's options for toggle valves on our needle valve options. Or I'm sorry, a toggle handle on a needle valve option. A toggle handle gives us some ability to position a valve open or closed, and it can lock in an open position. With regard to locking, ball valves can have a separate bracket. As a standard, there's not a locking bracket on our ball valves. It's a separate function, but all of our ball valves do have a consideration to allow a padlock to be passed through them. And it's going to be one of a couple different styles. It's either going to be this one that has a bracket mounted to the stem, or there's going to be a lockout actually attached to the handle itself. And this engages with a different bracket inside of here to prevent it from turning. So locking is this one. Latch locking is kind of this style. In order to actuate this valve, you've got to engage this locking mechanism into the valve handle, and that allows it to open up, or it allows the release of this coupling to allow it to actuate open or closed. And then from a spring return standpoint, I hesitate to mention this because we kind of can offer it, we kind of can't. We've got a couple of suppliers that can make a mounting bracket for a spring assist manual handle on our ball valves. Traditionally, this is called like a dead man handle, that if you operated this valve to fill a vessel, to fill a bucket, fill a cylinder for sampling or for something else, if hypothetically the technician, when he's done gathering that sample, walks away and leaves the valve open, you don't dump the rest of the system media out. The spring assist allows that to close itself, to go back to a normally closed orientation. Swagelok does not make yet a spring return handle option. We had to go through third parties. Right now, I believe we've got 2 different ones that we interface with. None of them are domestic to be able to get a spring return option onto our ball valves. So in industry, they exist. From Swagelok, immediately, they do not exist. We need to go through a couple extra steps to be able to do it, but it is an option. As an option to manually actuation, there is pneumatic actuation. So this is, instead of using manual force, mechanical force, it's going to use an air pressure to either open or close the valve. Within our offering, there's a couple of different styles. It's either going to be a rotating actuator, like on our ball valves. It's going to rotate 90 degrees or 180 degrees if it's a switching valve. It could be a linear or an axial actuator, like with our bellows or diaphragm valves, that we're just lifting the seat in an axial or a linear orientation. And then there's an option to have it either spring return, like this one. So you apply pressure to it to get it to one orientation, open, we'll say. And then when we de-energize that actuator, the spring overcomes that loss of pressure and returns it to our de-energized state, which is traditionally a closed orientation. And then there's the double acting, which means that I need to have air to open and air to close. I've got to send different signals or have a switching valve that opens a valve and then closes a valve. Both are air. There is no spring in between there. What else is shown on here? This is a solenoid valve, which we can also supply. This allows you to electrically control your pneumatic signal. So you're going to supply air pressure to the top, and then you're going to trigger this valve with a electric signal. It could be a 5 volt, 10 volt, 12 or 24 volt, etc. To open a smaller valve in here to pressurize this or to depressurize the actuator cavity.
Hey, Derek.
Yes.
Can the spring returns be configured FO or FC?
Yes. Yes, they can. So FO and FC is fail open or fail closed. So that's a good question. When you're configuring these, there is an option at the end of that to identify the standard state, the de-energized state. We use NC or NO, normally open or normally closed, but FO and FC would be the same thing, a fail condition. And that would be essentially if your facility lost power, lost pressure, what state does that valve return to? In a system failure, does it return to an open condition or a closed condition? So typically you want your vents to fail open and you want your processes to fail closed. It's a good question. Yes, you can configure them in either of those two orientations.
While I have you stopped, are the solenoid valves available explosion proof?
Yes, we have a couple explosion proof options. I believe they end up being special. They end up being special ordered. They're not all stated in the catalog. There's some that are NEMA 4, 4X, 7, and 9. And then there's some that are class 1, div 1, but they're not all as a standard explained in the literature. So if you do have an opportunity that needs to have explosion proof or something else standard wise with solenoids, please let us know and we can make sure that we get you the right one. Any other questions on actuation? All right. These last couple go pretty quick. So the next thing we're going to talk about are check valves, our directional control valves. Want to talk real quick on crack and reseal pressure. When we order a check valve, there's going to be a nominal cracking pressure. It doesn't mean that it's going to be the absolute cracking pressure. So if we pick a cracking pressure of 1 psi, it doesn't mean that at 1 psi this valve opens all the time. The nominal cracking pressure is going to be an average, and it's going to be the average pressure differential between upstream and downstream to be able to open it. Usually it's a couple of psi, up to about 4 psi. There's also going to be that cracking pressure range. Obviously, that's identifying what your nominal cracking pressure is. The reseal pressure is going to be what is required to get this valve to reseat. So there's a pressure to open the valve, but there also needs to be a pressure to close the valve. And this can be one of two things, either a downstream pressure or an upstream pressure reduction. So if it's a heavier spring, usually it's an upstream pressure reduction that's got to happen. If it's a lighter spring, you actually need some downstream pressure, downstream is outlet, to get this to reseat, to get it to close. If you don't achieve either of those, the valve kind of sits in limbo and it kind of throttles back and forth. A couple of different designs of a check valve. The most common is going to be a spring check valve where you've got a poppet or some other sealing device that's powered by a spring to get it closed. There's also a lift check where there is no spring and you are a gravity dependent check valve. There's also a swing check, which I don't show here because Swagelok doesn't make one. It works similar to a lift check, except instead of having this this poppet that rises and falls. You have, if you were to look at it this way, instead of having this, you have a little disc that's hinged at the top. So as the flow comes in, it lifts this hinge up and out of the way, and then gravity kind of helps reseat it again. And when we look at the closure type, there's really just two different styles. You've either got a ball, as shown here, or there's a poppet. And a poppet is really anything that's not a ball. It's just a machine piece of stainless steel or other metal that's designed to make a seal against an O-ring or a different seat. Some check valves can be field adjusted. We always recommend when you're making any adjustments to a fluid system that your process is off, but you can change on some check valves the cracking pressure based on the tension that you put in the spring, or the compression rather that you put in the spring. So with the system off, this is just two backup nuts. So they're adjustable by an Allen wrench, and you can either add or reduce pressure in here to get it to open when you want it to open. Check valves, we'll go right into relief valves. Don't go into relief valves. So relief valves, similar to check valves, but different. They're going to operate based on the same pressure differential. Typically, your outlet is a vent because you want to get rid of any excess pressure in the system and vent it. Or seat. Our seal is going to happen right here between this poppet and this engagement. So even though they're doing similar functions, they are different components. We're going to go through them. A check valve is designed to stay open, which is kind of weird to think about when you think that the spring is actually trying to maintain this thing in a closed orientation. But they're also designed to close quickly so that you don't get backflow in the system. Typically, these are all low pressure, so just enough to prevent backflow. When we look at a relief valve, they're designed to be closed, and they only open when there's a certain process condition. That's going to be your pressure differential between, again, your inlet and outlet, but it's really a higher pressure application. So these have to close once your pressure drops. So why is this one closed and this one is open? It's really your spring intensity. This is a much lighter spring. A lot of these you'd be able to compress between your thumb and forefinger. When you look at a relief valve spring, these are very heavy springs. These are very difficult to be able to hand actuate. Most of them you can't. So with this spring force, these are designed to stay closed. This is going to require a lot of system pressure to open up. These are really light enough. The check valve springs are light enough to allow flow all the time through. So even though they're springs trying to maintain a closed orientation, check valves are designed to stay open. We're all clear on the different styles of relief valves. So relief valve, by definition, it's a spring-loaded valve that's actuated by the static pressure of the fluid. So we're not adjusting an open or closed orientation with a handle like we are with a ball valve or a needle valve. This is going to be system sensing to identify when to open or close. With a safety valve, again, this is going to be spring-loaded. It's actuated by the static pressure. Again, this is going to have a rapid opening or a pop action when you see that system pressure open. And really the poppet design, which is this gray box here, is really what's going to accommodate that. And we look at the surface area that's being acted upon here versus this one. As soon as this stem tip, if we call it that, comes off of that seat, we're exposing this entire surface area to this system pressure. So it's going to take this small, which lifts it off the seat, and then exposes it to the full surface area here, and that thing slams open. So you have a very rapid depressurization of the system. Relief valve, safety valve. A safety relief valve is still going to be spring-loaded, but it's then has a qualified discharge rate. The qualification is usually by PED or other third party, but and it's sized basically to reach its maximum flow within this right here, 110% of the set pressure. So it very quickly goes from closed to open to be able to make sure that we get that full volume out of there. From a Swagelok standpoint, Swagelok does not make a safety valve. We have a relief valve and we have a safety relief valve. We do not have a safety valve. Similar to needle valves, relief valves are going to have flow curves associated with them. This is so we know how quickly we're able to get that volume out of the system. These are almost like regulator flow curves. So what we're going to track is our inlet pressure on our vertical axis, the flow on our horizontal axis, and we want to know what the set pressure is through each of these different springs. So we're going to have the regulator or the relief valve series up here, identifying which color they're going to be. And then our condition that set at 200 PSI, really we're not seeing any flow. It's going to barely crack open. And then as we start increasing the flow or the volume that we're trying to get out of the relief valve, what you're seeing with these curves is what happens or what needs to happen to the inlet pressure to achieve that flow. So if we need to evacuate, say, 30 cubic feet per minute, and we're going to set it at 200 PSI, in order to achieve that, our inlet pressure is going to rise to about 280 PSI, 275. So we're going to see that. We should expect that upstream, which means that any gauges that we have, any transmitters, need to be rated to at least that pressure. Because if that's the volume we've got to evacuate, that's what's going to happen with this relief valve. If this one's not appropriate, maybe we go down to a larger relief valve, the R4. That's how you would read these curves, is knowing what pressure you're trying to have this operate at. We need to know what kind of flow we're trying to get out of a relief valve. It's not just pressure. So it's not a great practice to just find one that's rated on pressure and say, I'm going to put this 1/4 inch relief valve on this 4-inch line, because ultimately it's not going to be effective. You think of the volume that's going through the system and make sure that we don't have a condition that your system pressure, in order to achieve that flow, you know, you're still double or triple or 50% over what our set pressure design is. We want to make sure that they're appropriately sized, not only for the pressure, but also the flow that's going through them. And just like with regulators, all the flow curves are going to be with air, so we're going to have to convert them to the system media that you're running through the system. And I can help with that. Any questions on checker relief valves before we tackle excess flow valves? Excess flow valves are designed to prevent an entire system loss of media in the event of a downstream failure. A lot of people try and use a check valve for this. It's not going to work that way. That's not how they're designed. The best way to show how these work is to actually show a video. So we're going to see if we can do this. It's a rupture downstream.
Swagelok XS Series Industrial Excess Flow Valve helps protect against hazardous spills and environmental releases and improves safety. In its normally open position, flow is virtually unrestricted through the valve. If a line breaks downstream, the XS Series valve automatically trips to prevent the uncontrolled release of fluids from
system isn't off, but it is a much reduced flow.
When flow exceeds the XS Series trip range, as in a line break, the pressure drop created across it immediately moves the poppet to the trip position, reducing the flow to less than 2% of the trip flow rate. When the system is repaired, the XS Series valve automatically resets to its normally open position.
I like that video because I like to think of who in a system is wielding a knife like that, cutting through plastic lines or breaking lines with a baseball bat. But the reality is there are downstream failures that happen. It could be a line that blows out. It could be somebody accidentally stepping on something and shearing a valve off. So while the modes of failure are not expected to be a knife-wielding associate who's cutting through plastic, the function of it is the same. So we want to make sure that whatever is in this, whether it's usually it's not a closed volume. If you have a house line that you're concerned of just dumping the entire house line forever during this failure, you would put one of these in and then just have a reduced volume coming out of it. And it is sensing differential pressure across this. So when we look at how to size these, this is, for better or worse, our only collateral. Is you're going to have our flow, which is going through the system. It could be either air or water. And we have an inlet pressure. So there's a range in here that this valve is going to trip, that it can trip. Otherwise, it's either going to be open or you're going to be fully tripped, fully engaged. So that we're just slightly bleeding that system pressure off of there. What we publish in our literature is just this one curve. There's actually 3 different springs. So I would encourage you, if you do have an application for an excess flow valve, to let us know and not try and do it on your own, because there are some other pieces of literature that are not otherwise available to you immediately that we can help with. A lot of the applications that I've seen, the flow is way down here. We're using very limited flow, very small lines, and much smaller pressure. So buying the standard one will never trip. And it doesn't matter what you do, you could have that right off of your tank, right off of your system. Most that I've seen that are asking for an excess flow valve, they'll put them in the system and they will never trip ever. They're decorative. So if you have an application, please let us know. We'd be happy to help you size those. That is all that I have for you. Sorry that I went a little bit over, but at this point, if you have any questions, I would be happy to take your questions.
Just going to turn on the microphone for attendees if you do have a question. I know, Bill, I believe you had a couple questions. Factory certification.
Yeah, we have applications where the settings have to be done by you and sealed. So you didn't touch on any of that.
Derrick, you're muted.
There's an icon there. Found it. For a relief valve, you mean?
For a relief valve, and I was also curious for the check valves in case it was required for a check valve.
Okay. So yes, the relief valves are available with whatever set pressure you need to have on there. The set pressure is actually required for our larger relief valves. For the smaller ones, our instrumentation, you can get those without being factory set, but certainly all of those can be set from the factory ahead of time. Excuse me, and documented, so that you'll have what the system pressure was, and then as it was tested, you'll see that documentation as well. So for a relief valve, absolutely. For a check valve, it's less common. The process, excuse me, the process for a check valve is very similar. If it needs to open, and if we usually your check valve range is between like 50 and 350. So if there was one that you needed to say it's got to be 120 psi cracking pressure, we could have those factory preset as well. Check valves are much less common than relief valves. Relief valves are almost always. Any other questions?
I have one more, and that would be if you talked about lifespan of the valves, are there testing procedures you publish?
As far as how to determine cycle life, or how to determine leakage, or with regard to which?
Determining, I'd say leakage would be the big thing.
Um,
Other than the obvious.
Yeah, So I guess I'm not sure why I asked you to clarify, because no, we don't publish either. Either an expected cycle life or, I mean, your troubleshooting, there's a couple of things that you're going to do as a standard anyways. So knowing your system, knowing, or at least you being familiar with your system, you know what you should expect through each of the valves. Obviously, if you have a leak from the process to the exterior, you're going to either hear it as a gas or you're going to see it if it's a liquid. So as a general walkthrough, every time period that you do, whether it's every shift, if it's every week, etc., part of that practice, I would assume, involves checking the area, making sure that there is no liquid on the ground that could have been caused from the system media. When we look at gases can be a little bit tougher, so there are some leak detection things that we could offer, either using a leak detection media like Snoop, or a different third-party reagent, something that's like soapy water that you can put on the connection to see if you're getting a leak across it. There's ultrasonic technologies as well. And if you don't have the means, we'd be happy to come out and take a look at a couple of the valves that you may have in question. From a cycle life standpoint, that's a much more difficult thing to test against. We think of all the different system media that could be running through it at the different process conditions, pressure, temperature, what's happening downstream, how often you're cycling the valve. All of that's going to kind of play into what to expect from any valve. So there's kind of an accepted range, but that range is enormous. But it's all going to depend whether it's, a slurry or a gas, and high pressure versus low pressure, and actuated twice a year versus actuated every 30 seconds. All that's going to play into what to expect from the valve. Not sure if that answered your question or made it more confusing to you.
No, that's fine.
Any other questions? All right. At this point, if anybody else has any other questions that they don't want to ask publicly or otherwise, hopefully you still have my contact information. Feel free to send me an email or give me a call, and be happy to engage with you offline.
Yeah, and just to let everybody know, we will be sending out a recording of the presentation, and remember that does have Derrick's contact information in there, so if you do rewatch that and have a question that comes up afterwards, feel free to reach out to him. Thanks again to everyone for joining us today, and we wish you all a safe, healthy, and enjoyable holiday season.
Thanks, everybody.